Now we analyze the dynamic circuit when R equals 0. Set the initial value of the capacitor as 3 volts. Now we need to look at the voltage nodes of 1 and 3. You can see that the whole capacitor voltage and the inductor current are oscillating waveforms with no attenuation. The reason is simple, because the whole circuit has no loss term. We need to point out that the inductor current is 0 when the capacitor voltage is with the maximum value, and the capacitor voltage is 0 when the inductor current is with the maximum value. This feature only exists in the case of no damping. By using numerical method, we have analyzed in detail the theoretical expressions and the waveform of the UC and IL in case of overdamping, critical damping, underdamping, and no damping. Then in the case of these 4 different situations, what is the difference of the change speed of the capacitor voltage or the inductor current? Next, we still use simulation to illustrate it. In order to compare the change speed of the capacitor voltage in case of overdamping, critical damping, underdamping, and no damping, we need to give the voltage nodes of 12, 8, 4, and 1 at the same time. We simulate it. The green line is overdamping, the blue line is critical damping, the purple line is underdamping, and the red line is no damping. Because the oscillation will not occur in case of overdamping and critical damping, so their speed of energy change are slow. The speed of energy change in the case of underdamping is significantly faster than the previous two. Of course, the fastest one is a no damping oscillation. Similarly, we can see the change of the inductor current. Now we need to draw the voltage node 14, 10, 6, and 3. Now the red line is overdamping, the green line is critical damping, the blue line is underdamping, and the purple line is no damping. Similar to the previous discussion, you can find that the change speed of no damping is the fastest. Next is underdamping, critical damping, and overdamping are the slowest. The case of no damping is almost impossible in the practical applications. So we use the case of underdamping more. Underdamping has 2 aspects of applications. First, because its speed of energy change is faster, so we can get faster waveforms. Secondly, it involves the capacitor's voltage and the inductor's current, or the charge or discharge process of the electric field energy and the magnetic field energy. So we can get the designated capacitor voltage forms or the inductor current forms with the proper element parameters. We will discuss more in 58. At the end of this lecture, we will discuss several parameters of the second order underdamping dynamic circuit. We will discuss them using UC as a variable. We have defined R over L as 2 alpha and 1 over RC as omega 0 square. Since it's underdamping, so its B square minus 4AC is smaller than 0. We give the definition of omega D. Here we give the definition of alpha, omega 0, and omega D. Alpha is called as attenuation factor. Please look at the general solution of UC. Alpha appears in the exponent term. That is, the number of alpha determines the speed of attenuation. So it's called the attenuation coefficient. Omega D is called attenuating oscillating frequency. Through the previous simulation, we can see that the waveform of the circuit is a damping oscillating waveform in the case of underdamping. So the angular frequency of the waveform is called the attenuating oscillating frequency. For omega 0, you can see that now with no damping oscillation, in the case of no damping or no resistor, its oscillation frequency of the whole circuit. Because of the expression, we can draw the right triangle about the three variables. It's like this. Here we ask you two questions. The first question is that R, L, and C, these three values corresponding to alpha, omega 0, and omega d, respectively, what kind of numerical relationship is among them? The second question is how RL and C change so that the whole circuit changed from overdamping to critical damping and then change to underdamping and then change to no damping. If students if you have deep understanding about the two equations, it will help you understand second order dynamic circuit. Well, that's the end of this lecture.